see me blob blob. I'm gonna close this real quick. Okay, so that's not the only thing that's gonna be kind of off schedule this week. I'm gonna have a wonky schedule this week because well, actually, technically Tuesday night, I'm flying out to Brookhaven in New York to go to a particle physics planning committee. And then I'm also staying there for basically the week. So I'm gone basically. Let's do the green. What color is good for gone? Orange. So I'm gone on the 12th, on the 13th. I mean, technically on the 14th, 15th, 16th also. But the one that concerned you guys are the days I'll be missing a class basically until the 18th. Okay? So don't miss me too much, maybe, right? But the plan is to basically still go through the chapter. And so I have video lectures from last semester. And Dr. Makhtari, who's actually the department chair, has volunteered to come in to work with you on worksheets on Thursdays, Thursday and Monday. And that way you guys still get the same worksheet experience as you would have if I was here. Okay, so I gave her the answer, and then, you guys will be able to solve these magnetic induction problems that we're going to talk about this week. And so that's going to be happening this week where, instead of, so on Wednesday, this Wednesday, you won't have to come to class, but you do have to watch the video lecture. And then on next Tuesday, also there's no class. And then you just have to you just have to watch the video lecture. But then the worksheet days, you're still coming in. Does that make sense? And that way you guys can get the worksheet done. And I'll be back next Wednesday to start the next chapter. Okay, so the plan today and tomorrow is actually to basically cover enough stuff on chapter 30, which is the next chapter we're going to be on, so that you can do the worksheet on the 13th, and also the video lecture will cover stuff so you can work on the worksheet on the 17th, which actually is worksheet 17. Okay, any questions about that? Concerns? Yeah, Lydia?
Why are we doing chapter 32 when we get
After that,
chapter 39?
because it makes more sense to me, because I like it that way. No, so chapter 32 is on alternating current circuits, and chapter 31 is on electromagnetic waves. And so what happened is that after we cover this thing called induction, so we know what an inductor does, it actually makes more sense to me for us to put it in a circuit and see how it works versus going to electromagnetic waves, which is actually about optics, which is what we're going to cover before the final. Hopefully it'll make sense. I don't, so if I wrote, I mean, some textbook will have it the other way. Some textbook have it this way, so there's a contention amongst textbook writers, like which one to put first. But they're both related to each other, the induction thing. And so what's going to happen is that we're going to finish up chapter, right? So we did 29, 30, right? We're going to do 32 and 32, 32 and 33, right? That's our 4 chapters before, where the heck is the midterm go? Oh, before midterm 3, right? Which is actually on the 8th, okay? I think you guys like the midterms on Monday, right, instead of Thursday, right? That way you guys have the weekend to study, right? Because I could have put it up here, but let's just put it on Monday. And then we'll have our final the week after that, so it's a pretty tight schedule for the next 6 weeks, okay? And unfortunately, I'm basically gone for one of those weeks also, which is not helpful, right? So, but this meeting got scheduled like before the semester even started, and been trying to plan out this video lecture plus worksheet thing together with you guys, okay? So you'll be able to watch the video lectures at home, and then be able to do a worksheet when you come to class on this Thursday on the 13th and then the 17th. I'll send you guys everyone an email about the schedule, okay? And that way you know when to come, when not to come. All right. All right, busy. All right. So before we get started today, once again, since we're starting a new chapter, let's talk about another American physicist Mary Gellert. So she's in particle physics, which is sort of what I do. Well, I mean sort of. I am also in particle physics, but she's a theoretical physicist, meaning she actually can look at what the experiment measures and be able to predict the future, like, oh, what you should expect in the future, which is kind of a cool thing to be able to figure out just by, doing some math, just like what you guys are doing in the class, and figure out, what type of new physics there could be in the future and how experimentalists like me should look for it. So they basically guide how we built our experiment. And she basically predicted the mass of the charm quark. So this is stuff inside protons, okay? And also predicted the B quark, which is the bottom quark. So these are subatomic particles that she was able to predict that their existence and their mass in order for experimentalists myself to build the right experiments to look for them. So that's pretty cool. And she's actually pretty local, so she worked mostly at Berkeley, which is where I'm going to be working this summer also. Okay, so let's start chapter 30. Before I start, any questions about the schedule or particle physics, B quarks, theoretical physicists, Mary Gallagher? Yeah. They will be posted online, but I think is the policy still like a full credit or half credit for those? Because you're not in class doing it, right? You do okay. All right. Since I'm gone also, right? I'm also not showing up. Okay, so we can do full credit for the worksheet this coming week at least. Okay. All right. That's why I'm worried that none of you guys are gonna show up, right? And then it'll just be like Anthony there working by himself, which is not cool. um, well, but then okay, so you're going to have an actual excuse, okay? So you have to have a doctor's appointment or something like that, okay? You have to have an actual excuse. You can't say, oh, I don't feel like going to school today, all right? Okay, all right. So something with a document, okay? All right. So because I have an excuse, right? I have to go to I'm not just hanging out on the beach, right? Okay, so let's start talking about chapter 30 for the next 25 minutes that we have left. Um, Chapter 30 is on this idea of electromagnetic induction. Okay, so remember the previous chapter we learned about magnetic fields, right? We focus only on magnetic fields. So what are magnetic fields like? How do you calculate magnetic force? What makes a magnetic field? How do you calculate all this magnetic field stuff, right? This is just to figure out what magnetic fields are. Okay, and then one of the neat thing about last chapter was that there's this thing called Ampere's law. You guys remember that? Right? Where you can actually figure out, right? If you have some current going around and then you have some loop that's, usually a circle, right? Nothing this complicated, right? That you can figure out what is the magnetic field around this Amperian loop, right? If you know what the current going through that loop is, right? Right? And this implies that while if you have a current, it creates a magnetic field, right? So current makes magnetic field, which is what Oersted first found out, right, when he accidentally placed a compass on a little circuit that he made for an electricity demo. What we're going to do now is that we're going to do it the other way. So actually, instead of current creating magnetic field now can create current, which is a kind of wonky thing, which is you don't expect that, because right, the magnetic force only acts on things that are charges that are moving. And we're going to see how this happened when this guy, Michael Faraday, and we're going to be familiar with his name because there's going to be a law named after him, where what he did is that he had some a little battery with a little loop in it. So just imagine this is a wire, right? And then he's just kind of like moving this around, right? And he actually detected that there's some current that's created by this little loop. And you might think, okay, well, I mean, you have a current going around in here that creates another current somehow. That makes sense, right? Current creates current. But then what he did is he just took some magnets, okay? took some magnets and just kind of move them around, just jiggle them around. And I have a little simulation about this in a second here. That also creates a current somehow. So somehow, right, you don't need a battery, right, at all. You just take a little magnet and then you just move it around, and then you can actually create a current, okay? This is if you're moving the magnet around your little loop. You can also take your little loop and leave the magnet permanent, meaning just, you know, in place, and then you can move the loop around. That also creates a current, okay? I'm going to show a little bit better demonstration of this in a second here when this loads. Right, come on. Okay, so this is a simulation called Faraday's Law. So if you want to play around with it, feel free to do that. Hopefully it loads. Come on, don't be mean. There it goes. Come on, full bars. Full bars. Okay. I'll just click on the link instead. Let's see if the one from the on OneNote loaded. Nope, it's just not refusing to actually load. Sometimes this works, sometimes it doesn't, but then the website always works. Okay. My internet's just slow. It's connected. Great use of time, right? This is a useful demo. That way you guys can actually see this in action if this thing ever loads. Hopefully it's not just loading ads, right? There it goes. Play this. Okay, there it goes. Okay. So what I'm going to do is I'm going to put there's a little light. So there's some coil. So this is a closed loop, right? And the reason for multiple coil is that then you actually get multiple turns in like your solenoid that we learned about last chapter, right? What I'm going to do is I'm going to take this and just kind of move it around and see what happens. Okay. 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 So if I move this in and out of the coil, right, then the light bulbs, you know, simulating it's lighting up. But even if I'm moving it, you know, on the edge without even going through the coil, the light bulb still lights up. Okay. What I'm going to do is I'm going to draw the field line of my little magnet, right? Remember, magnetic field goes from the north pole of a magnet and ends at the south pole of a magnet. Okay. And you guys tell me as I'm moving this left and right, what am I doing that's causing the light bulb to light up? Anyone want to venture a guess? What am I doing? I mean, what's changing? Right. So the fields are either more fields are going into the coils or less fields going into the coil, right? So the neat thing is that if I go out here, if I move it towards it, the light bulb lights up. If I move it away, the light bulb also lights up, right? So it's not like more fields mean more lights from the light bulb. It's like the change in the field that causes the light bulb to light up. Okay, and that's what we're trying to show here. We can even go up and down, and it'll still do this, right? But it's not as bright because of that. So that's my 2-minute demos that take like 10 minutes to load. Okay, so let's go back to the lecture. So let's not look at that anymore. Okay, and we're going to figure out how we can actually quantify that. But the first thing is that what we're going to do is maybe make a simpler system. Let's just figure this out, how this works in a much simpler situation. Okay, and this is the next section called motional EMF. Okay, right. So let's say I have just a piece of metal, right? Just some, you know, piece of bar, you know, iron bar or whatever, right? Or aluminum, whatever material is made of. And I have it in a magnetic field, right? What I'm going to do is I'm going to move this little bar to the right with some velocity v, okay? So according, right, to what we learned last chapter, the magnetic force, right, is just the charge cross-producted with the magnetic field, okay? So therefore, I'm going to do my 1, 2, 3 count, right? So 1, the velocity is in this direction. The magnetic field is going into the board. So if I was a positive charge, I would have a force acting upward on me, right? If I was a negative charge, I would have a force acting downward on me, right? Does that make sense? Right? 1, 2, and then 3 going up. So that's interesting because since I say this is a metal bar, right? It's not magnetic, but it's just a piece of metal, right? Remember the idea of a metal is that it's a conductor, and a conductor allows charges to move around inside, right? So if you have a little positive charge in here, it's going to move upward, okay? And then if you have a negative charge here, it's going to move downward. And you know, everyone know these days in reality it's actually the electrons that's moving. Therefore, it's actually the negative charge that's moving around, not the positive charge around moving around, right? But if an electron moves from here to down here, it's as if a positive charge moved the other way, right? This is sort of the symmetry thing we always have to deal with because of Benjamin Franklin deciding that positive charge is actually what's moving. Okay. So what we're going to do is that what's going to happen is that as you move this around, you're going to develop a slight negative charge down here and a slight positive charge down here because, right, this motion caused a magnetic force, F of B, right? That's going to push the positive charge up and the negative charge on the bottom. But that doesn't end there, okay? Now we're going to have to connect this to the electric field also. What happened is that while now we have positive charge here, negative charge here, right? When you have a positive charge in one spot, negative charge in another spot, it's going to create an electric field, and that electric field is going to be pointed downward. So what's going to happen is that as you move this little bar to the right, over, you know, as it goes around, right, you're going to have a balance of force between magnetic, that's pushing the positive charge up, and then a electric force that's pushing the positive charge down. So we're just modeling this with positive charges, right? Okay. So how can we quantify this, okay? Well, the way we figure this out is that you draw a free body diagram, right? Which the book mostly did for us already, right? So we have a positive charge in there that has a magnetic force pointing up, an electric force pointing down, right? When the system is in equilibrium, meaning the magnetic force and the electric force are balanced to each other, right, the charges stop moving around, right? So you're not going to have charges moving around. So we're going to have this kind of stable equilibrium where the net force is going to be 0, and this implies that the magnetic force plus the electric force, right, they're going to have to add up to 0, right? Since the magnetic force and electric force are in opposite direction to each other, that means their magnitude are equal and opposite each other. Well, their magnitude is equal to each other, their direction is opposite each other, right? Well, to calculate what the magnetic force is, right, we just have Q V cross B. The electric side, right, is just whatever the charge is times the electric field, right? Okay. This cross product is nice to figure out because the angle between V and B is actually 90 degrees, right? So we have V this way, B going into the board, right? This angle right here is 90 degrees. So the cross product between them, right, just gives you QVB, right, without the vector stuff, okay? If you just want the magnitude, right? The cool thing is that the charges actually cancel out, okay? So here we're going to have, up here, I'm going to write this on the right, the velocity of the bar times the magnetic field is going to be equal to the electric field. In other words, the electric field that's created inside our little bar is just how fast we're moving the little bar times the magnetic field that's applied to it, that's permeating through it, okay? So neat thing is that, well, if V goes to 0, right, let's say we stop moving the bar, right, the electric field goes away, and all those charges just kind of migrate back to their original position. Okay, so this is kind of a neat thing. So this is a temporary created electric field. Okay, we're going to call this, because it's an electric field that's created due to the motion, right? We're going to call this the motional EMF, right? Because it's a moving thing creating an electric field, right? And this electric field, we're going to convert this to a EMF. Remember EMF? EMF is a voltage, right? Not a force. Okay? The electromotive force, which is a voltage, if you want to calculate what that is, all you have to do is take the electric field you got in here, which is, right, the magnitude is just the velocity times the magnetic field, right? If you want to calculate the voltage from the top and the bottom of this bar, you just have to multiply that by L, right? That will give you the change in voltage along this little metal bar that we just created, okay? All right. And the nice thing is that, well, if you have a voltage, that means it just kind of acts like a battery, right? If you have something that gives you a constant voltage, right, as long as you're moving this thing at a constant velocity to the right, right, you're going to get a battery. So basically, this is a way to create a battery just by moving metal around in a magnetic field. Right? So that's sort of neat. Okay. So let's do an example. Okay. We're going to do a circular one. Okay. So let's say we have a metal bar, right, that's pivoted at some central location, right, and it's going to spin around like this, right? Hopefully this will be a reminder of something that we use to generate power. Okay, if not, then we'll talk about this afterward. Okay, so what's going to happen is that as this little bar moves around, you're going to create an induced induced electric field inside here, right? And we're going to figure out what the direction is, that the positive, why does the positive charge goes out and the negative charge goes in? We're going to figure that out, okay? But that's going to create an induced EMF, and I think that's what the problem is asking for, to figure out what is the potential difference between the ends of the bar, meaning what is the potential here minus here. That means it's a potential difference between these two guys, right? So we want to figure out delta V over here, right, which is exactly from this equation. Okay? So from our previous discussion, we can have V, B, L already. Okay? So, but in this case, right, we're not moving it at a constant velocity V. We're rotating this thing at some constant angular velocity omega. So how do I convert V to omega? Anyone remember? V to omega. So one way to remember is that, well, velocity, right, has to have units of meters per second, right? Omega has units of something per second. Rate is typically radians, but you can take out radians if you want, right? So whatever's on the right-hand side, right, is missing something that has a unit of a meter, right? The only thing that's relevant when you go in things, have things going around in a circle, is the radius, right? So that has the radius, okay? So we can actually make a substitution in here. So it's almost right, right? Right? It's omega times r, not omega divided by r. So that's how you figure out the units, okay? Okay, so this is actually omega times r times b times l, okay? All right. So that will be the potential difference that you would get if you have a little blade spinning around, right, in a magnetic field, okay? And this is actually how a electric generator works, right, such as a windmill. The blade itself up here, they're not the one that's actually generating power, because these blades are not in a magnetic field, but this little shaft here, I think they're called, this axle here is connected in here to basically a reverse electric motor, where you have a magnetic field between the two, okay? So you have some north pole magnetic field, some south pole magnetic field, right? So you have some magnetic field in here, right? Where a little shaft, just like what we did up there, is spinning around, right? It's just spinning around, and therefore it's actually generating a potential difference for you when we're making it. When you have the blades of the windmill, collecting the energy from the wind to turn the thing, to turn the blades, which connects to this axle, which actually turns the stuff inside the electric generator to produce this motional EMF for you. Okay. There are other examples that I won't have time to go through, such as measuring the Earth's magnetic field. So you can actually do this on Earth's magnetic field. Earth has a very weak magnetic field. It's basically 1/10,000th of a Tesla, right? That's why that's why it works on a compass. But it's such a weak magnetic field, you really can't generate power out of it. Especially when you put these two magnets next to each other, you get like 10 Teslas worth of magnetic field. So you want that instead. Okay. Okay. Any questions about that? Oops. Any questions about creating electric field and potential difference when you have objects just moving around in a magnetic field, right? Which is sort of neat. Okay. What we're going to see is that, well, if we quantify things a little bit more carefully also, right, we can actually figure out not just the potential difference between these two sides, but also connect them to a little circuit. When you connect them to a little circuit, it'll create a current. Okay? So this is a very similar picture as above, right? We have a bar. Just ignore the wire for now. We have a bar. We're going to be moving it to the right. Okay? But instead of just having it, floating in the air somehow, we're going to connect them to two wires that are in this kind of like, U shape. Okay? It's not connected on the other end. Okay? It's just this long wire like this. Okay? Okay. So this makes an electrical connection, right, between the top of the bar to the wire, and it goes all the way around like this, and it goes to the bottom of the bar and goes around. And that's how you create a little loop. Okay? So this is known as a slide square electric generator. It's not very practical, but it's a very easier thing to explain. Okay? So as we learned before, let's go back up to our motional EMF calculation, right, is VBL. Okay? So the EMF that's going to be generated if I have this thing moving at some velocity V, it has some distance length between the two rails, L, and it's inside some magnetic field that's perpendicular to V. Right, that's going to create a motional EMF, right? That's equal to V times V times L. Okay. So if you have a little circuit like this and you want to figure out the current, the thing you need to know is that, well, I'm going to need to know, well, what is the resistance of my little bar, right? We're going to model that as a resistor, okay? We're going to model the bar as a resistor, and then we're going to make the wire basically, something with very little resistance or almost no resistance, okay? So all of the resistance is in this little bar, okay? So if you want to figure out the voltage drop across a bar, oops, right? What we can do is just make this into our circuit. So remember, this thing acts as a battery, right? Okay, this thing acts as a battery. So I'm going to draw a little battery here, right? Since now we're modeling this little bar as a resistor also, so it has some internal resistance to it, right? So R, EMF, okay? If we apply Kirchhoff's law here, we're going to see that, well, the current going through, the voltage drop across the resistor is going to be I times R, right? But that's going to be exactly equal to just this EMF. And then the EMF is from up here. So I over R equals to VBL. If you want to figure out what the current is, it's just VBL over R, right? So just a little algebra steps, okay? All right. So this allows you to generate a current in a loop once we make this little connection, okay? You can even find so you may think that, well, remember one of the things we learned last semester is that if things are moving at a constant velocity and no forces are acting on it, right, it'll go at a constant velocity. It's as if I tap this over, right, it'll just, let's say this wire is very long, right, it will just generate power for me forever, right? But that doesn't happen. And that's because what's going to happen is that as you move this bar, as this bar moves to the left, there's going to be a magnetic force that's going to be pulling back on it. And unfortunately, I'm going to have to talk about this tomorrow. Okay, so I didn't cover that much today. So let's do that tomorrow, and hopefully we'll cover enough stuff to